Hi guys, today I'm going to be talking about the first part of atomic structure, which is an introduction to atomic structure. So first I would like to give you a summary of everything that I'm going to be covering in this video. So the first thing that we're going to be discussing is the particles in an atom, which is basically O-level knowledge, so I'm going to be recapping that. The next thing that I'm going to be talking about is mass spectroscopy, which is completely new A-level knowledge. And then we're going to be looking at some key definitions, most of which have already been discussed in O-levels. So the first thing that we're going to be talking about is what exactly an atomic or proton number is. So this shows you the number of protons that are present in the nucleus of that element. And now we're going to be looking at the different subatomic particles that you have. So there's a proton, electron, proton, neutron, and electron. So we have the symbols for these over here. So the approximate relative mass for a proton is 1. For a neutron it's 1. And for an electron it's either 0 or this number over here. And you can also write down negligible. The charge on a proton is +1. The charge on a neutron is 0. And the charge on an electron is -1. Now it's very important to not write no charge for a neutron, just write down 0. So this was mainly O-level recap. Now we're going to be talking about the behavior of particles in an electric field. So if you have a positive plate over here and a negative plate over here, and you release a beam of particles containing protons, electrons, and neutrons, the neutron beam is going to go undeflected, so it's going to pass straight through and its direction will not change. However, since protons are positively charged, they're going to deflect towards the negative plate, as a positive charge attracts a negative charge. And electrons, which are negatively charged, are going to move towards the positive plate. And one more thing to notice is that since electrons are lighter, they're going to deflect more than protons. Now we're going to be talking about the second section, which is mass spectroscopy. Now this is used to determine the relative mass of atoms and the relative abundances of individual isotopes. And a mass spectrum, which we're going to be taking a look at on the next slide, tells us 3 important things: the number of isotopes that are present, the relative isotopic mass of each of these, and the relative abundance of each isotope. So what you see over here is a mass spectrum. On the x-axis, you have mass over charge over here. In our syllabus, since the main charge that we're going to be looking at is just 1, the x-axis just represents the mass for us, because anything divided by 1 is just going to be that number. So now we're going to be looking at the isotopes of iron. So if you take any sample of iron that contains all of these isotopes, this is the spectrum that you're going to get. On the y-axis, you have the percentage abundance of that isotope. So for 54, the percentage abundance is going to be 5.82, as it's shown in this table over here. For 56, the percentage abundance is going to be 91.06%. For 57, it's going to be 2.19%. And for 58, it's going to be 0.33%. So usually in your exams, they give you this table and they ask you to calculate the relative atomic mass. Or in some questions, they might just give you the graph with values on the y-axis and ask you to calculate it. So the way you do this is, you multiply the percentage abundance by the relative isotopic mass for each isotope that you have. And then you divide that by 100 because it's a percentage sign, and that's going to give you the relative atomic mass, which is 55.8. And if you look at the periodic table, they usually round it off to 56. The next section that we're going to be taking a look at is the definitions. So the first definition is relative isotopic mass. Now, relative isotopic mass is the mass of one atom of an isotope relative to 1/12 the mass of a carbon-12 atom. Relative atomic mass is going to be the weighted average of all the different isotopic masses that you have. So for example, if you have an element that has 3 different isotopes, the relative atomic mass, or the AR, is going to be the weighted average of all of those. And like the previous one, this is going to be relative to 1/12 the mass of a carbon-12 atom. A relative molecular mass, or the MR, is going to be the sum of all the relative atomic masses that are shown in the molecular formula. So for example, if you have a compound like H2O, which is water, then you're going to take the AR of water and add it to the AR of oxygen, and that's going to give you the relative molecular mass, which is 18. Now, the term relative molecular mass is used for covalent compounds, and the term relative formula mass is used for ionic compounds. However, both of them have the same definition. Now we're going to be looking at the definition for the mole. Now, 1 mole of a substance contains the same number of particles as the number of atoms in exactly 12 grams of carbon-12. And this number of atoms is the Avogadro's constant. So the Avogadro's constant refers to the number of particles in 1 mole of a substance. And since this is a constant, the exact value for this is 6.023 into 10 to the power 23 particles. And the definition of an isotope is that isotopes are atoms of the same element with the same proton number. That means the same number of protons, however, different nucleon number. This means that the thing that differs is the number of neutrons that are present in the nucleus.